Okay, so good morning, students. Let me hope you're all fine and let me hope you enjoyed your Easter. So, by making this video, I suppose that all of you have watched the first two videos, and I suppose that by now, when I talk about a first order differential equation, you know what that means. You know what a differential equation is. You can tell whether a differential equation is homogeneous or non-homogeneous. You should be able to tell whether a differential equation is linear or non-linear. Tell the degree of a differential equation as well as the order and so on. So, in this video, I want us to start by looking at how to solve a first order differential equation. There are several methods which we can use to solve differential equation, but that depends on the nature of the differential equation that you have. So a given differential equation may be solved using method A, but may not be solved using method B. So it depends on the nature of which differential equation that you have. And now, the first nature of differential equations, which we are going to look at, are what we call the simple separable differential equations. And what do they mean? So we have that a first order differential equation is said to be separable if it is of the form dy dx equaling to g of x over f of x. So this form means that you have a differential equation whereby the numerator is a function or a polynomial having only x as the unknown, and the denominator is a function having only y as the unknown. Or it can also be that the numerator has a polynomial of only y as the unknown, and the denominator has only a polynomial with x as the unknown. So as long as you have a differential equation equaling to a fraction whereby what is in the numerator is a polynomial or a function of only one variable without mixing up different variables, then we are interested in those kind of polynomials. And do you know the reason why they are interesting? Is because if you do cross multiplication, for example, in this case, if we cross multiply, then we shall have f of y dy equaling to g of x dx. That's what we are interested in. So given a differential equation of this form, can you be able to cross multiply such that you have your function with y dy? So meaning all the y's are on one side with the dy equaling to all the x's are on one side with the dx. And with this kind of simplification, we have that when you integrate both sides, that's why you have integral f of y dy equaling to integral g of x dx. What we get is, okay, suppose when you integrate this function f of y, we get capital F of y. Remember from your A level that whenever you integrate a function, you must add a constant. So if you integrate the left hand side, and we get f of y plus a constant which I'm calling c1 equaling to, when you integrate the right hand side, suppose we get g of x plus a constant which I'm calling c2, then it is useless to deal with two constants c1 and c2. So instead of adding the two constants c1 and c2, we shall be just saying that integrate the left hand side, get what you get, which is f of y equaling to integrate the right hand side, get g of x, and then add just one constant, which is c. So that is how we are going to be dealing with these equations. Okay, so a separable differential equation, we've seen that is the one whereby if you cross multiply, you get a function which has y dy equaling to a function which has x dx. So as long as you have your differential equation and you can be able to rewrite it in that form, in this form, where the y is with the dy and the function with x is with the dx, then we shall just be continuing like this. You integrate, add constants, and you're done. And that method is what we call the method of separation of variables. Let's look at an example. Our first example is this one. dy dx equals to y minus 1 over x plus 3. So in the numerator, we have a function with only y as the unknown, while in the denominator, we have a function with only x as the unknown. So now the question is, can we be able to rewrite this differential equation such that the function of y is being multiplied by dy equaling to the function of x being multiplied by dx? So let's do cross multiplication and see. If we cross multiply here, we shall have x plus 3 dy equaling to y minus 1 dx. But we are interested in having dx being with a function of x and dy being multiplied by a function of y. So how can we make sure this is possible? See, what if you divide both sides by x plus 3, even this side by x plus 3? On the left, we shall be left with dy equaling to y minus 1 times dx over x plus 3. So now realize that we have dx, and then this dx is being multiplied by a function 1 over x plus 3, which is a function of x. So that is somehow promising. But now the challenge is now this function of y. So we should take it the other side. And how can we take it the other side? On the left, by dividing both sides by y minus 1, y minus 1. And when you do that, you have dy over y minus 1 equaling to dx over x plus 3. So at least now in this form, the y's are on their side and the x's are on their side. So when you achieve this point, then the next step will be to integrate both sides. I'm not going to go into the details of differentiating and how to differentiate. I refer you to Backhouse 1 and Backhouse 2 A-level mathematics. Okay, so what do you get when you integrate? So this is the same as having 1 over y minus 1 dy equaling to integral of 1 over x plus 3 dx. When you integrate 1 over y minus 1, you get natural log of y minus 1. I hope you still remember those basics of integration. And how about on the left hand side, when you integrate 1 over x plus 3 with respect to x, you get natural log of x plus 3, and then plus the capital C, which is our constant. But since we are solving a differential equation dy dx, that means we want to get the value of y. So this is not the simplest form. So how shall we get y alone? This time it's under natural log. So it has that when you introduce e, which is the exponent on both sides, then you shall have exponent natural log of y minus 1. It will be equal to exponent natural log of x plus 3 plus c. But this exponent natural log of x plus 3 plus c can as well be written as, can be broken into 2, as you can see here, because from the rules of logarithms, if you have the same base, then you add the powers. Okay, so here E, when you add this ln of x plus 3, then plus c, we go back here. So I'm just rewriting this second step as this, that this is the same as having E natural log of x plus 3 times E to power c. Okay, so E to power natural log, the E and the natural log will cancel, and we shall remain with y minus 1 equaling to E and this natural log will cancel, and we shall remain with x plus 3, then times e to power c. So let us let e to power c to be equal to some constant, because I don't want to keep writing two things, e to power c, e to power c. So let's just make this one to be k, where k is a constant. So that would mean that y minus 1 will be equal to k times x plus 3, and then when you make y the subject, this is going to be our final solution. So that is the first example. Let's look at another example. Still we are looking at the method of separation of variables, where I put the y's alone and the x's alone. So in the second example, we have the differential equation dy dx equaling to 6x to power 5 minus 2x plus 1 over cos y plus e to power y. Let us cross multiply. When you cross multiply here, we shall have cos y plus e to power y dy. So you can see that on the left hand side, all the y's are together. This has y, this has y, dy, equaling to, then this will give us 6x to power 5 minus 2x plus 1 dx. So the x's are also on their side. So that means we can move to the next step, which is integration. And the integration, you have to do it on both sides. What do you get when you integrate cos y? Now this, I refer you to A-level mathematics. When you integrate cos y, we get sin y plus. When you integrate e to power y, we shall remain with e to power y, equaling to, integrate this, what do you get? So that is 6x to power 5, add 1 to the existing power and divide by the new power. When you do that, you end up with x to power 6 minus x squared plus x plus a constant of integration. So here, can we be able to simplify to get y? No, I think in this case it's not easy, but at least we have all the y's on their side. So you can say that this is the solution to this differential equation. And we've got this solution by using the method of separation of variables. Okay, I have one last example here, where they have told us to solve the differential equation square root of y dx plus, into brackets, 1 plus x dy equaling to 0. And this time they have given us the initial condition. So that means this differential equation is an initial value problem. I hope you still remember what an initial value problem is from the previous videos. So the moment they give us these initial values, that means we can use them to find the value of the constant c. Okay, so let's begin by solving the differential equation. So this time we have root y dx plus 1 plus x dy equals to 0. But we need to have the y's alone and the x's alone. So we begin by taking this term on the right hand side. And when you do that, since it is positive here, the sign will change and will become a minus. So that's why we have square root of y dx equals to minus, into brackets, 1 plus x dy. But we need the x's alone and the y's alone. So we begin by dividing both sides by negative, into brackets, 1 plus x on both sides, and also divide both sides by square root of y, square root of y. So when you do that, we are going to end up with this step. Please try that and make sure that this is what you get. So at this point, realize that you have now all the x's on their side and all the y's on their side. So we begin the integration, not forgetting this negative sign here, so that this negative sign, I've put it here. Integral dx over 1 plus x equaling to integral dy over square root of y. So what do you get when you integrate 1 over 1 plus x? That will still be natural log of 1 plus x, not forgetting our negative sign, equaling to, now, the integral of dy over square root of y. This can be written as dy over y to power half. Square root of y is the same as y to power half. And now at this point we have 1 over y to power half, which if you want to write y in the numerator, it is the same as y to power negative a half dy. And when you are integrating, we add 1 to the existing power and then you divide by the new power. So what is y to power negative a half plus 1? That will be y to power a half. So the new power is a half, so we divide by 1 over 2. And when you divide this, realize that it's the same as having the 2 will go up since it's a fraction in the denominator. This is simple mathematics which you should work out and get. So when you divide this, you get 2 times y to power half, which is same as 2 root y plus a constant. So now we have negative natural log of 1 plus x equals to 2 root y plus a constant. Now, we need to find the value of this constant by making use of the initial condition. The initial condition here means that when x, what is in brackets is the x. When x is 0, then the value of y equals to 1. So that's what I put here. Now let's substitute x equals to 0 and y equals to 1 in our solution here. That negative natural log of 1 plus x equals to 2 root y plus c. So when you put x equals to 0 here, you have negative natural log of 1 plus 0 equaling to 2 root y. What is y? Y is 1 plus a constant. So square root of 1 is 1. So that means on the right hand side here we shall have 2 plus c. Now how about on the left? Natural log of 1 plus 0. 1 plus 0 is 1. What is natural log of 1? Natural log of 1 is 0. You can check that from your calculators. So that means this side we have 0 times negative 1, which is 0. So we have 2 plus c equals to 0, which implies that the value of c will be negative 2. So that means in our solution we have natural log of negative natural log of 1 plus x equaling to 2 root y minus 2. Okay? So that's what we have here. But now this 2 root y minus 2, we have a common factor. So this can be written as 2 into root y minus 1. But remember, I want to remain with y. So we shall divide both sides by 2, even this side by 2. And we get negative natural log of 1 plus x over 2 equaling to root y minus 1. We want to remain with y, so we take this minus 1 this side, so that we end up with this fraction plus 1 equaling to root y. How can we remain with y only if we have square root? We square both sides. So when you square both sides, you end up with y on the right equaling to everything here squared. So this will be our solution. So we've solved the differential equation using the method of separation of variables. And in this case, since they gave us the initial condition, we are able to use those initial conditions to find the value of the constant C. So briefly, that's how we use the method of separation of variables. As long as you can rewrite your differential equation such that you have the x's on one side and the y's on their side. Then after that, integrate both sides. If you have initial conditions, use them to find the value of the constant C, and you're done. Okay, so with those 3 examples, I want you to try these 8 questions. Try solving these 8 questions using the method of separation of variables. In the next video, I'll be showing you a different case of differential equations, and hence we shall look at a different method of solving differential equations of a certain form. Alright, I hope you enjoyed the video. Thank you so much for listening. Feel free to try these questions out and send me your solutions so that I can have a look. Alright, have a nice time. Bye bye.